So the next unit in the topic of structure and bonding is the final SL unit, that of metallic bonding. So it'll be quite a short one. So by the end of the unit, you should be able to know that metallic bond is an electrostatic attraction between positive ions and delocalized electrons, the strength of a metallic bond and what it depends on, what alloys are, and I might even add a little bit of a dancing theme to that. Explain the electroconductivity and malleability of metals, explain the trends and melting points of metals, and explain the properties of metals in terms of non-directional bonding. So the final type of bonding we will look at is metallic bonding. So what is metallic bonding? Well, a metallic bonding essentially is the electrostatic attraction between a lattice, so we already looked at lattices in ionic bondings, of positive ions and delocalized electrons. Okay, so we have here a positive ion, and there's all these delocalized electrons, and it's basically an attraction between the positively charged positive ions of the metal and the sea of electrons. Okay. So the strength of a metallic bond depends on two major things. Okay, the first one would be the strength of a metallic bond increases with the charge of the ion. Okay, so for example, the melting point of sodium is around about 100 degrees Celsius. Okay, that explains why it forms a ball when you react it with water. And the melting point of magnesium, which has a 2+ charge, is 650 degrees Celsius. So you can clearly see the difference between the particular ions there. Okay, and the reasoning for this, of course, is all about the effective charge between the delocalized electrons and this nucleus. Okay, and the strength of a magnetic bond also increases with the smaller size of an ion. Okay, so for example, sodium, even though we made fun of it last time for being such a small melting point, has of course the melting point of 100 degrees Celsius, whereas potassium has a melting point of 64 degrees Celsius. Okay, it's got a smaller radius, so a bigger radius. So it's going to have less electrostatic interactions between the delocalized electrons. Okay, so it's going to have a lower melting point and weaker metallic bonds. So in terms of metallic bonding, there are two special properties which you need to be able to explain. Okay, metals are both conductors of electricity and are malleable. They can be kind of bent into shape. So for conductivity to occur, a substance must possess electrons or ions that are free to move. We've already seen that in ionic bonding. Metals and graphite, and also ionic salts in solution and melted, contain delocalized particles. At least in terms of metals, it will be electrons, and they are therefore excellent conductors. Metals are also malleable, which means they can be bent and reshaped under pressure. This is due in part to the close packed layers of positive ions that can slide over each other without breaking more bonds that are made. Okay, and we will now see that in the next part of the video with a short animation. So another aspect of metallic bonding is the ideas of alloys. So alloys are a mixture of metals and one or more other element. Usually it's a metal, and this mixture actually has increased strength, durability, hardness, resistance to corrosion, or magnetic properties, depending on the metals and other elements involved. This is due to the different elements being of different sizes, preventing this easy sliding between the atoms. Okay, and I'm just going to show you with this link a short video around being a superalloy, which you will have to find the link in your own time. It's called Dance Your PhD, a superalloy is born. So if you search for that on the internet, you will surely find it. So here are some examples of some alloys. We have brass, which is a mixture of copper and zinc. So copper is unreactive reasonably, and zinc gives its kind of nice luster to the doorknob. Steel is a mixture of iron and carbon, so this carbon actually adds strength to the actual metals because steel is actually quite brittle as a metal. So just to review, I've created a table here of the different types of intra and intermolecular bonds that we have looked at. Okay, so the first one we're going to look at is, or we looked at, was the covalent. Okay, and they could be broken down into both molecular and giant covalent. Okay, and that happens between two strong electronegative atoms. So, for example, fluorine. F2 would be an example of a molecular covalent bonding, and giant covalent with diamond or graphite. Then we have ionic, and then this is between one strongly electronegative atom and one weakly electronegative atom, essentially between a metal and a non-metal, and that would be example would be sodium chloride. And then we have metallic, two weak electronegative atoms, okay, like two metals basically. And the more positive the nucleus, the better, the more electrons, the better. So that would explain why magnesium has a higher melting point than sodium. Then we have hydrogen bonding, which is an electronegative atom from one molecule and a hydrogen atom from another molecule. So that electronegative atom would be either nitrogen, oxygen, or fluorine. The more polar the bond, or the dipole, the better. Okay, so HF would have a higher boiling point than, say, ammonia for that reason. Then we have dipole-dipole forces between two polar molecules. So hydrogen bonding is a special case of a dipole-dipole force. And again, the more polar, the better. So hydrogen chloride would be a higher melting point than, hydrogen bromide will be a higher melting point than hydrogen chloride, because you've got that polarity, but you also got an interaction with the final example, which is London forces between two non-polar molecules. Okay, and the more electrons again, the better. So, for example, a helium molecule, or methane, or oxygen. Okay, the more electrons, the better, because you get a larger instantaneous dipole forming, greater polarization. Okay, so that's pretty much a summary of the different bonding that we have looked at.